Welcome to CHE 2101, Chemistry 1. To secure these 2 credits, you have to clear a very specific set of hurdles. Your final grade breaks down like this: 30% rides on the midterm, 10% on quizzes, 10% for assignments and presentations, 10% for simply showing up, and the final 40% comes down to the final exam. To pass those exams, you first have to understand the premise mapped out right here in this network diagram. Chemistry sits at the exact center. It is the hub that links all other scientific disciplines. You can't grasp food science, medicine, or nuclear physics without first understanding how matter behaves at a base level. Long before we had university grading rubrics, humans were already practicing this science. We isolated dyes like indigo from plants, forged new alloys like bronze by mixing copper and tin, extracted alkalis from ash to create soap, and fermented carbohydrates to produce alcohol. Manipulating the physical world is our oldest survival tool. Formalizing those ancient raw processes into a strict, measurable science is exactly what Chemistry 101 is designed to do. This triangle diagram illustrates the 3 distinct perspectives chemists use to view the universe: the macroscopic, the microscopic, and the symbolic. To operate as a chemist, you have to translate information continuously across these 3 domains. The macroscopic domain is everything large enough to sense directly, like this iceberg. The microscopic domain reveals atomic reality. Gas molecules are disorganized, while solid ice is rigidly locked. Finally, the symbolic domain uses formulas like H2O to describe these states without drawing them. Together, these 3 domains give scientists a complete translation tool. By understanding invisible microscopic rules written in symbolic language, we can predict exactly how massive macroscopic objects will behave in the real world. When observing the physical world, chemists first look for physical changes. This happens when a substance alters its form, but its core composition stays identical. Melting ice or crushing a pill are physical changes. The material looks different, but atomically, it is the exact same stuff. A chemical change is an entirely different event. In this process, atomic bonds actively break apart and rearrange themselves. The original material is destroyed, and completely new substances form instead. To prove a chemical change actually occurred, you need observable evidence. You check for the sudden appearance of a solid precipitate falling out of a liquid solution. You look for drastic color shifts, sudden spikes or drops in temperature, the emission of bright light, or the release of volatile odors. This shows these reactions in practice. Panel A, copper and nitric acid emit brown nitrogen dioxide. Panel B, cellulose combustion releases heat and light. Panel C, iron oxidation turns meat brown. Panel D, dark new substances form as a banana decays. The universe is constantly breaking down and rebuilding itself. Identifying exactly what type of change is happening right in front of you is the first step to controlling it. These rules govern human survival. Take human metabolism, for example. When you eat bread, your body initiates a chemical change, breaking carbohydrates down into glucose. That glucose reacts with oxygen to produce carbon dioxide, water, and ATP. ATP is the molecule that carries energy to every cell in your body. The stability of our medicine also relies on managing chemical changes. If you expose aspirin to moisture, it undergoes hydrolysis, a chemical breakdown. The aspirin fractures into salicylic acid and acetic acid. That acetic acid is exactly why expired medicine develops a sharp, vinegar-like smell. We engineer these reactions to keep populations safe. Pumping chlorine into a water supply creates HOCl, or hypochlorous acid. This is a strong, highly reactive disinfectant that destroys the cellular walls of viruses and bacteria. In larger treatment plants, we add lime to contaminated water to force toxic dissolved metals to form heavy, solid precipitates, which we then physically filter. Chemistry is the mechanism running quietly in the background of everyday life. It dictates how our bodies generate energy, how long our pharmaceuticals remain effective, and how we keep our infrastructure safe to use. To prove any of these theories in the symbolic domain, you need a rigid language of measurement. Chemists rely on the International System of Units, SI base units like meters for length, kilograms for mass, and Kelvin for temperature. We scale these units using strict prefixes, ranging from mega for the massive millions, all the way down to femto for the submicroscopic fractions. But physical measurement is never perfect. There is always uncertainty. When you measure liquid in a graduated cylinder, you have to read it from the lowest point on the curved surface, the meniscus. Your eye, the glass, and the angle introduce a margin of error. Because of that error, we use the rule of significant figures. The rule is absolute. Any result you calculate can only be as accurate as your most uncertain, least precise measurement. To keep the math honest, you have to round your numbers aggressively. Here is how rounding applies. For two significant figures, 31.57 rounds up to 32. For 3, 8.1649 rounds down to 8.16. For 4 significant figures, 0.051065 rounds down to 0.05107, and 0.90275 rounds up to 0.9028. Mastering the central science requires a split skill set. You need the imagination to visualize how invisible particles construct the macroscopic world, and the rigid mathematical discipline to prove your theories on paper. Learn the rules, watch the changes, and check your significant figures. Class dismissed.